to crank out ships, mainly to be used for troop transport, ocean transport, supply. There was an insatiable demand for ships by the U.S. Navy in the Second World War. And Henry Kaiser started churning them out. And he produced this method of churning them out using welding procedures rather than bolting them together, so they could be done very, very quickly. They would crank them out over here in Richmond, they would throw them into the water, and they would take off. And a very large number of them, ships built in other places too, particularly out of here, these so-called Liberty ships, got into cold water and cracked in half. A number of them cracked in such a way that they could be saved. Some of them cracked, sank to the bottom. Some cracked before they got to the Golden Gate Bridge. And some of them just disappeared. We assume they cracked, but nobody knows what happened to them. So the Navy got really concerned about this. And after the war, they started a very big program, Office of Naval Research. And a lot of it was centered right here in Berkeley. Earl Parker, who was still in faculty when I came here, built a 2 million pound tensile test machine to test fracture and so on. The solution to this, or the understanding of this, involves two things I'll tell you about. One is fracture mechanics, which came out of this ONR program. After the second, British plane, they invented it, but they're not telling the truth. It was in this country. George Irwin and a few other people were the originators of fracture mechanics. The other thing was the notion of the ductile-brittle transition, which had been around a while, but nobody ever quite put two and two together. And I'll tell you about that too. Let's start out with fracture mechanics. So suppose that I take a sample here, and in the sample I have a crack. Now let me load the sample up with some external stress that, if this sample were complete, we kind of did this in the first D45 lab, would be the nominal applied stress. Well, now the applied stress is fine as long as the body is contiguous. But right here at this crack, for geometric reasons, the solutions of the equations of elasticity give you a great big boost, a substantial intensification in the stress here at the crack tip. In fact, if your applied stress, just the nominal load divided by the area of the sample, is sigma A, the stress at the crack tip turns out to be a geometric factor. Square root of A is the crack length. I think in these slides sometimes I use A and sometimes I use C. Here's A. Divided by rho, which is the crack tip radius. What I mean by that is if you take any real crack, no matter how sharp it looks, when you blow it up in a microscope, you'll see the tip is curved, and there's some effective radius rho. Now look at the consequences of this. As rho goes to 0, the stress at the crack tip will increase without bounds. Of course, you can't do that because eventually it would exceed the yield strength of the material and get some deformation. But in theory, this thing goes without bounds. So if you have a sharp crack, then you can break this material, even at a relatively small value of the applied stress, because that applied stress gets ferociously amplified here at the crack tip, unless something like plastic deformation intervenes to blunt it out. So you take a brittle material. Well, you know, for example, how do you quote cut glass if you're going to shape a pane for a window? You don't take a saw to it, you just shatter the glass. You take a little scribe, you run it over the surface, and you take the glass and just tap it, and it breaks right there. What that little scribe did was it put in some cracks. Not very big, but glass is a material with a very high yield strength. So you get a sharp crack in a piece of glass and you've been loaded up by tapping it. And even though the load you put on it may not be very high, the load here at the tip of that crack is huge. And so boom, there it goes, it pops. And that's basically what fracture is all about, and it's amazing it took them as long as it did to figure that out, but they did. Here's just an example from a calculation done some years ago. Here's a crack. This was done for a specific purpose in the spring, so 100 pounds it would load up. You take the crack and you start loading it up. This is kind of like the experiment you did in the first T45 lab, this finite element calculation. And you see, in this case, you fix the length of the crack and increase the applied stress or the load. And as you do that, you see the stress field getting bigger and bigger and bigger, and the stress here at the crack tip getting more and more and more intense. And the stress here at the crack tip, even under fairly small loads, is some 5 times the nominal stress out of the material. So it's very easy to get large stresses at a crack tip just by using the geometry of the crack. Well, the crack length is also an issue. So in this case, I would do the same spring, same calculation, where we took the crack, fixed the load, I forgot what it was. Anyway, we fixed the load, and I just grew the crack. You see as the crack gets longer, the stress builds up and up and up until finally it becomes very, very big out here. So you can, if you have a crack in the material, you can load that crack up to the point that it just goes, either by increasing the load on it, and if the crack is sharp, that load at the crack tip is going to be huge, or you can increase the crack tip load by extending the crack, letting it grow until the load becomes so big until it breaks the material. Well, let's get to fracture toughness. How are we going to describe this? The simplest, there are various complicated ways to do fracture mechanics. I've always liked the simplest one, and it's always worked very nicely, particularly when you start trying to design steels and such things that have electric toughness. This is the most convenient way to look at it. Let's let sigma be some inherent fracture strength, such that the material here at the crack tip is going to start breaking if the stress ever gets to sigma b. The crack will therefore become unstable when the crack tip stress sigma t is equal to sigma b. And if the crack ever becomes unstable because of the load you've got on it, it's going to really be unstable. If I start to grow this crack, the crack gets longer. As the crack gets longer, the crack tip stress goes up. So if I ever get the crack tip stress on here that's big enough to propagate the crack, unless something else intervenes, that crack is gone. This sample is broken. So this sample is going to break by crack instability when the crack tip stress is equal to the breaking stress sigma b. That says that what we really care about is what is the value of the applied stress, the nominal stress, the overall P over A on the sample when the crack goes unstable. So I want to know what is the value of sigma A when sigma t is equal to sigma b. So I just plug in the equation on the last page and I solve for that, and I get that the breaking stress, and we call this the critical stress sigma c, that's the value of the applied stress when the crack goes unstable, is equal to Q minus 1, that's a geometric factor, I'm not going to spend much talking, depends on the shape of the crack geometry. Breaking stress, square root of rho divided by square root of A. And this is my measure of the critical stress, the stress at which this crack's going to go unstable. Now, if I look at that and I say, well, I'd like to have some material property that lets me calculate this easily. My problem is that on the right-hand side of this equation, if I'm going to do sigma c and do this theoretically, I would have to know the breaking stress, which depends an awful lot on the microscopic mechanism of fracture, and I have to know the crack tip radius, which depends on what, if any, plastic deformation do I get as the crack loads up. So these are things that not only are difficult to predict, they're very difficult to get hold of experimentally, individually. So what I do is I say, while I'm really going to have real trouble getting hold of either one of these numbers by itself, their product turns out to be rather easy to measure. Because all I have to do, let me call their product K, KC. Let me call their product the fracture toughness. A lot of people put a 2 pi in here, let me keep it simple. Call the product the fracture toughness. Then let me just do a test. I put a crack in of known length and known geometry. I load it as sharp as I can make it, load the sample up until it becomes unstable. So I've measured sigma c, I've measured Q, and I know A. So I can therefore measure the fracture toughness Kc. Now that's the product of a couple of things I'd have trouble measuring individually, but I don't really care because what I want to know is this. I'm going to be able to predict the breaking stress. So this is what's called the fracture toughness. The problem I have, it's only half a problem for reasons I will not tell you, is that this fracture toughness is not yet a material property. And the reason it isn't is that the fracture toughness depends on the geometry of the sample that I'm testing. Suppose I take a sample and crack it, load it up, there'll be some plastic deformation usually here at the crack tip, and I take samples of various thickness, and I measure the fracture toughness as a function of the thickness of the sample. What I'll find is that the fracture toughness depends on the thickness of the sample, and the dependence looks something like this. There's some fuzziness here at the beginning, but then the fracture toughness drops off monotonically as the sample becomes thicker until it asymptotes to a value K1C, which is called the plane strain fracture toughness. Now, why is that happening? It's happening for the following simple reason. Remember that back here in the fracture toughness has got in it this crack tip radius. Now, the crack tip radius will change if plastic deformation occurs to blunt the crack tip. Since blunting the crack tip lowers the stress, and since Le Chatelier's principle, the second law of thermodynamics basically, says if you put a load on something and anything happens, the thing that happens is going to try to drop the load. If you push on a table, it moves in the way you push it because it wants you to stop pushing on it. The same is true of a crack tip. Since the way I can decrease the load, the stress at a crack tip, is by blunting it, raising rho, then any plastic deformation that happens there will act in a direction that raises rho. So the more plastic deformation I let happen at the crack tip, the higher crack tip radius is going to be, therefore the higher the fracture toughness. If I take a sample that is very thin, then I can always get plastic deformation here in the plane of my plate, coming off at 45 degrees, normal plastic deformation. If the plate is very thin, I can also get plastic deformation through the thickness of the plate. But that also wants to go up at 45 degrees, and as the plate becomes thicker, that shear line that I would have to deform on to get this thinning in the thickness of the plate gets further and further away from the crack, out of the material that's way out of the stress field. The consequence of that is that as this plate gets thick, I lose this lateral deformation, and all I have left is this deformation in the plane. That condition is called plane strain. All of the strain associated with the crack tip is in the plane because I can ignore the thinning in the perpendicular direction. When that happens, all of a sudden the thickness effect is going to disappear. The degree of blunting will be the same no matter what the thickness is, and I get a constant value. And that's called the plane strain fracture toughness, and that is a material property. And that's what people measure, and that's what people tabulate. Now, that's actually not so bad. You may say, well, most ductile metals in most applications are not thick enough to have plane strain conditions. So in most ductile metals in most applications, the fracture toughness is going to be up here somewhere. So you say, guys, this is terrible. I don't know how to calculate the right value. It doesn't really matter. What matters is that the toughness of my actual sample at any thickness cannot be less than the plane strain value. Anything that happens here will make the toughness greater. What I want to do is to calculate my breaking stress, my critical stress, the design stress, the stress I cannot reach without causing this thing to fracture for a given crack size. So let's look at that. Suppose I calculate that, assuming the fracture toughness is K1C. I'll get a number. The true number, to calculate the true number, I would insert the real fracture toughness K. But K is greater than K1C. So the actual breaking stress in my material is larger than the number I calculate by assuming the plane strain fracture toughness. So I've got a built-in factor of safety here. If I design something, pick the worst crack that could possibly be in there, put in the plane strain fracture toughness, and use that to find my breaking stress, I'm safe. And what you want to be doing when you're designing things not to fall out of the sky, you want to be safe. Being accurate is not nearly as important as being safe. Of course, you can get to the point where you're so far off accurate that the part weighs too much and the plane won't get off the ground, but that is not a problem we've had to deal with. So this is how you use fracture toughness. Well, using fracture toughness, so what do? One thing we can do is use tough materials. Many parts, most of the parts of your automobile, many parts of aircraft, helicopters in particular, are actually not designed to fracture toughness at all. And the reason you can avoid designing them to fracture toughness is suppose you take apart, like, some gear or shaft or something in your automobile, and suppose you go back and you put the you put in the fracture toughness, you consider the worst crack that conceivably be there, and you calculate a stress. You don't have to worry about this crack instability stress unless it is less than the ultimate tensile strength. Because when you reach the ultimate tensile strength, the thing's going to break in plastic deformation, and it doesn't matter that if you could continue the stress, it might propagate a crack because it's already broken. So most things, what you do is you go find materials that are so tough that you don't have to worry about unstable crack propagation because the design of the part is such that it's going to break in ultimate tension before crack's going to propagate to failure. So an awful lot of things are designed to the, do I have it here? Well, yeah, sigma star is greater than sigma u, designed to sigma u. An awful lot of design is done that way. So what do you do if this gives you an unsatisfactory design? And where it often does is in critical parts in aircraft. Because in aircraft, well, it's becoming more true in automobiles and other things now, but in aircraft in particular, you've got to worry about how much the thing weighs. And you can't just thicken the wall to create a huge safety factor, because if you do, the plane won't get off the ground or can't carry any cargo or people when it does that. So that, particularly in aerospace, and that's where the real push came, you have got to design to crack safety. And in fact, the original Air Force program back in the 1960s that looked at this, the title of the program was Have Cracks Will Fly. The problem that really brought the Air Force to put in a multi-million-dollar program on using fracture toughness and design was the F-111 aircraft. The F-111 aircraft, the fighter bomber, was the first swept wing aircraft. You would change the angle of the wing once you took off for better flight. So you have huge stresses on the wing box. And they started losing F-111s because of fracture in the wing box. So they said, we got to do something about this. So they did this big program, and they said, okay, let's do the following. Let's inspect for manufacturing defects. Now, these days in advanced engineering, there is a huge field. I don't think there's a course on it in the Berkeley campus, there ought to be. But there's a huge field, an enormous technical society, which is non-destructive testing. And one of the principal things that guys in non-destructive testing do is they use various techniques to find out if you've got any cracks in materials. So they said, let's inspect these things to see if cracks are there. There are various techniques, dye penetrance, x-rays, acoustics, that you go looking for cracks in material. Then what they did, none of these non-destructive testing techniques are perfect. So they said, let's find what we can detect with the techniques that we can fairly easily use. So they did. So you take the technique you're going to use for non-destructive testing, and you let A star be the largest crack that can't be found. You say, look, if the crack's bigger than A star, anybody following the book can find it. But if it's A star or less, maybe it can't be found. You assume that such a crack is present. You give it the worst possible geometry, and you then design your limit load based on the worst crack that can be present, fracture toughness geometry. You make sure that your applied stress is significantly below that. And if you do that, you're safe. To show you how well our military works, however, after spending millions of dollars and coming up with a brilliant program to do this and documenting that it would work, They then realized that the way the wing box of the F-111 was designed, you couldn't inspect it without disassembling the whole airplane. So what they did was they grounded the F-111 and went to other fighters that are now designed. One of the criteria in designing a high-tech machine has got to be inspectable, because if it isn't inspectable, you can't use this kind of fracture toughness design. So that's how you use this fracture toughness design. Well, if you're going to use this kind of fracture toughness design, you, of course, it's critically important that you use the best materials you can possibly use, the best toughness you can possibly use. So the thing we've got to work on next is what determines the toughness of a material. And that gets us back into the other problem that they ran into over here in Richmond in the Second World War, and that's the ductile brittle transition. It turns out that you really can say there are two things really kind of govern the fracture toughness. One is the yield strength. For reasons that I'll tell you about more specifically later, the fracture toughness monotonically decreases as the yield strength goes up. So you can, in fact, always improve the fracture toughness of a material by dropping the yield strength, almost always. You lose fracture toughness when you raise the yield strength, and this is a very serious problem in structural materials because you want strength. If you don't have strength, the thing's going to fail by yielding. So you're looking for the best possible combination of strength and toughness. The thing that really affects toughness, however, is the fracture mode. I'll do mechanism next time, for just about a time, but just real quickly. You can fracture a material in microscopic modes that are ductile in the sense that they involve a lot of plastic deformation, or brittle in the sense that they involve almost no plastic deformation. If you have to deform the material significantly to fracture to propagate a crack, you're going to have fracture toughness. If you don't have to deform the material significantly if it's brittle, you get a low fracture toughness. It turns out in steels, in fact in all BCC metals, some FCCs for a different reason, there is a ductile brittle transition. For reasons I'll tell you about next time, at high temperature, these materials are ductile. There is a fairly narrow temperature range at which the fracture mode changes and then become brittle, and K1C can drop by an order of magnitude, just like that. Here in Richmond, in the Second World War, it turned out the ship plate that they were using was being tested in Richmond at normal temperatures, like outside, 60 degrees or so. The ductile brittle transition of that steel was about 50 degrees Fahrenheit. So they were testing it right here. They would then put it in the ocean, right here. And problems ensued. And the recognition of ductile brittle transition was the other piece of the puzzle. This was a contribution actually the British really did make, although they've been around a lot longer than that. You can find papers on the ductile brittle transition from the 19th century, but people didn't put two and two together until fairly recently. And this was the other part of the problem. So next time I'll tell you about fracture modes and the ductile brittle transition and strength and toughness and the rest of fracture. Okay.